So, just a question, do you see
Yes, we do.
the presentation and do you hear me well?
Yes, perfectly. Yeah.
Okay, thank
So,
you very much.
let me introduce Radek Cibulka to the audience first. So, our next speaker is Radek Cibulka. He is from University of West Bohemia in Czech Republic. So, he will be talking about ranges of nonlinear operators. So, Radek, the floor is yours.
Okay, thank you very much. I would like to thank the organizers for giving me the opportunity to speak here because I think that the whole workshop is wonderful. And my talk is about something different compared to the previous one because I will not speak about optimization directly, but I will try to make some connections with it as well. So my talk is based on a continuing work with Marian Fabian and Tomáš Roubal, and I will write what is it about. I have some mapping F, say from some set X space, for example, freshest space into another freshest space, for example, or in finite dimensions, and I have some subset omega in X, and I want to solve the equation. So I want to find for given y, so this is given, and I want to find an x. So the question is whether there is an x in omega, which can represent constraints, and I will discuss particular cases of this set, such that f of x equals to y. So this is what I am speaking about, and one more comment that I will have also some subset gamma of y, and my y's will be inside gamma. So the question is whether for each right-hand side from a given set, you can find a solution satisfying the constraints on x. So in principle, I have constraints on y as well as constraints on the solution set. So this is the general outline of the talk, and I will start with rather abstract setting, but don't be too scared because I will come into finite dimension very quickly. So assume that you have two mappings. So I have some F and G, and I am able to say something about the mapping G or solvability of the nonlinear equation corresponding to G. So, for example, I have some sets in Y, so it is here, and for each y inside this set, I can find a solution inside omega. So this inclusion means that for each right-hand side in quite large set, I am able to find a solution which satisfies my constraints. For G, so I am able to solve something like this, and I have another function, say f, and the difference between G and f is not big. So this is hidden in this set. So roughly speaking, I am able to solve this equation for a bigger set of right-hand sides, and G and F don't are not too much distinct. So here this can be something like order of the approximation or something like this. So I can view this as the case that G approximates my F. So in applications, G should be easy, should be simple, and the corresponding equation should be easy to solve. And I want to deduce from this something on solvability of the second equation, so corresponding to the second mapping F. And if you have this assumption, then if either your preimages are convex or the inverse of G has a continuous selection. So this condition simply means that your G has the inverse, which may be set valued, but you can select in continuous way with respect to the changes of the right-hand side. So you have continuous selection for the inverse, then you are able to solve also the second equation, but for right-hand sides, which are in a set which is smaller a bit than the previous one. Compare this and this. So this set is bigger, this set is smaller, but you can solve this equation and find a solution in such a way that your constraints represented by the set omega are satisfied. I am not going to discuss the proofs of this statement, but just to know, if you are familiar with Kekutanis fixed point theorem, then within the Frechet spaces framework, this extension goes to Glicksberg. So if you have the first assumption, the convexity of the preimages, then you apply this Glicksberg extension. And if you have continuity of the selection of the inverse, then you can apply directly Schauder-Tikhonov fixed point theorem to get this result. So this is quite innocent result, but I want to spend a lot of time on the consequences of this innocent result. So let's make this precise in this case called Frechet-Montel space. This is the space which has additional Heine-Borel property, which means that closed bounded subsets are compact. So if you have a Frechet space, you can generate the topology with some sequence of seminorms. So you can assume that they are somehow increasing, as in this case, and suppose that you are able to solve linear problem. So for each right-hand side, which satisfies some constraints on the seminorms, I am able to find a solution of this linear equation. Then you have a second mapping, the nonlinear one, which is continuous and such that the approximation of f by the linear mapping is very good. For example, this goes back to Grave theorem and so on. Then the conclusion is that you are able to satisfy also the nonlinear equation, so to find a solution x, and here you have also distance estimate. So you know how the solution changes with respect to the changes of the right-hand side. So this is something more in case of Banach spaces, then this is called metric regularity of the mapping, or pseudo-Lipschitz property of the inverse. And just a small remark, my set is always closed convex, and in the previous slide was also compact. So if I go back, here I had compact convex set. So the difference is that here you have closed convex set only, but you have additional Heine-Borel property, which somehow ensures that in fact you are working with compact sets. And how to prove this? Your mapping G from the innocent statement will be simply the continuous linear operator, and you define these sets in such a way then that your mapping A maps omega at least to the set gamma plus the tightness of the approximation. So this is the approximation error, and this omega is now somehow intersected with the set which corresponds to the size of the solutions, and when you make this intersection, then this set is not only convex but also compact because of the Heine-Borel property. So you can apply the innocent statement, and you end up with graph theorem in Fréchet-Montel spaces. So I'm rather abstract so far. So just a small example of Fréchet-Montel space. For example, you can think about the space of infinitely many differentiable functions defined on some open subset omega of Rm, and you can define the seminorms in standard way in order to make this space Fréchet space. And of course you have here some norms of differential operators of arbitrary order, and this construction makes C infinity a Fréchet space, and more importantly, it's not only a Fréchet space, but this space has also Heine-Borel property because you have Arzela-Ascoli theorem. So this is one example where you can apply this abstract result. So for example, partial differential equations and solvability of these equations. So this is the first example, and let's go down. So from Fréchet space, I'm going down. So now to Banach spaces, yeah? So every Banach space is of course a Fréchet space, but you don't have only now not seminorms, but you have norm at hand, and your spaces are complete, of course. Then let's discuss the following problem. Assume that you have two mappings F and G which are close to each other in this Lipschitz way, and assume that my mapping G, which is the approximation, is uniformly continuous and has a Lipschitz selection for the inverse. So this selection is eta, and this selection is Lipschitz with respect to the changes of the right-hand side. Then the claim is that your mapping F is also uniformly continuous and have also Lipschitz selection. Of course, this selection is different, and the Lipschitz constant is a bit different. So here is C plus mu, and here is only C. So if you want this in the terms of Lipschitz constant, then this means that the Lipschitz constant of sigma is bigger because it's 1 over C. So this is corollary, and just again to show how the proof works. So you apply the innocent statement in function spaces. So my X will be the space of continuous functions from y to x, and y will be the space of continuous functions from y to y. And your set omega is defined in such a way that it contains Lipschitz functions. My set gamma will be Lipschitz 1 functions, but in y, and the approximation error is connected again with Lipschitz functions with sufficiently with a Lipschitz constant, which is chosen in particular way, so mu over c, and you simply produce new mappings by composition for the original one with my functions from the function space. Then the set omega is convex and again compact with by Arzela-Ascoli theorem. So you simply apply the innocent statement and you have this corollary. So this is the second corollary, and let's go down more. So now I am not in Banach spaces, but I am in finite dimensions. So assume that you have a linear mapping represented by a mapping A, and your A is surjective in such a way that you have some constraints on the solution represented by convex cone L, closed convex cone L, and here your right-hand sides are chosen to be in some prescribed cone in Rm. And assume that the approximation is again very tight, so then you can conclude that the image of the nonlinear mapping contains this set. In particular, this is image on the under the linear mapping, and of course you end up with something like this, which again means from which set you can choose the right-hand sides in order to have a solution. If you just want to define the property or call by some name, then you can call it directional semi-regularity. If my cone M here is the whole space, then it is semi-regularity or openness at a point, or metric semi-regularity or something like calmness property for the inverse. So this is the statement in finite dimensions, and again the application of the innocent statement is really straightforward. So you simply choose sets in particular way. So this is omega, this is gamma, and this is the error. And just one comment: the difference is that here you have some radius of my ball, and here you have linear dependence, so a constant times the same radius. Yeah, so this is precisely openness with linear rate or metric semi-regularity, so everything is fixed at the reference point. And one more comment concerning optimization, because yesterday we saw a lot of talks concerning some constraint qualifications. Then of course this type of semi-regularity yields something like constraint qualifications. For example, it gives you that the tangent cone to the image to the nonlinear image can be computed by the tangent cone to the pre-image. Yeah, so this is what we have seen many times yesterday, where dealing with some cones. So this is directional semi-regularity, and let's move on to some special case which somehow came to my mind from a project which I was doing with Department of Cybernetics, and it was about the stability of power injections into the electrical network, and you want to ensure that your network will somehow deal with the power injections, so you don't end up with blackout. So this omega here is represented by constraints, or the approximation of the constraints. Of course, in real networks, there are no convex constraints. The constraints are highly non-convex, but you can somehow approximate from inside by a compact convex set. And here, this means that you have a box with some endpoints. So the definition of ordered interval is here. All the inequalities are coordinate-wise. So this is precisely that you have gamma plus the error. So in the applications, it says that you solve the linear problem and you are close enough to the nonlinear mapping. Then if your range of power injections, for example, is within this range, then you are able to find the solution, which means that you satisfy the constraints of the network. Again, the direct application of the innocent result. So this is purely finite dimensional case, and just a small remark that you can ask how to ensure this first inclusion, the solvability of linear equation for each right-hand side from a box. Then this is of course done and well known, I think, but I can somehow present it. So for example, if your omega is a polyhedron, so bounded polyhedron, so you can represent it in this way, then you can, and you have some matrix which is full rank, then if you find these deltas in such a way that this inequality is satisfied, then you are sure that this box is inside the linear image of my polyhedron or polytope, if you want. And here the plus is simply positive, and here minus is negative part of the matrix inside the square brackets. So this is just to show you that you can actually compute the box inside the linear image. And of course, the question what we were facing was to inscribe the largest box as possible, because you want to make this as large as possible in order to have this as large as possible, and as a consequence to have the as large as possible for the range of the power injections. So this is pretty applied problem, and if anybody is interested, I can send him some details personally, or some more references provide. So this is just concerning corollaries of the innocent statement, and I hope that you see that the statement is not so innocent as it appears. Somebody can say, okay, compactness, convexity of omega, it's really bad, strong assumption, but you can obtain very, very interesting result from this. And just to end my presentation, just a comment that we generalize this to the case when you approximate by a set of mappings. So, for example, in finite dimensions, as before I have shown you, then your set A can be, for example, the Clark generalized Jacobian, or the pseudo-Jacobian in case of continuous functions. And the difference is that you have a bunch of candidates which approximate your mappings, and all of them have to be have to satisfy this bigger inclusion. And the thing is that your error is now dependent on you. So you give me a point, and I have to find one approximating operator in such a way that I satisfy the error request. So, for example, in case of generalized Jacobians or pseudo-Jacobians, by look and so, then this condition is connected with mean value property. So, for example, Clark generalized Jacobian has mean value property, so you can do this, and the conclusion is again something about the range of the nonlinear operators. Ingredients of the proof, as in the case of the statement number 1, Glicksberg extension is the tool, but you have to combine it with line segment principle and Michael selection theorem, where the target space is Frechet. So this it really holds, and for example, can be found in quite old student's book by Jon and Zisler, and of course much later it's published somewhere in a journal by different authors, but this really holds. So to end up, I would like to give you a homework. Try to formulate the similar corollaries as in the case of the statement number 1, so for the statement number 2 at the end. And I would like to thank you for your attention, and especially I am grateful to many people who I was cooperating with. So here are some pictures. The first one is Marian Fabian, the second is Esen Donchev, the third is Alex Kruger, the fourth is Vladimir Veliov, and the fifth is Alek Joffe, and the last one is my PhD student who somehow makes very, very good progress. So I think that in future we will meet with him in several conferences. So thank you very much for your attention, and that's all I want to say today.
Thank you very much, Radek. It was a nice talk. So do we have any questions for Radek?
Not a question, just thank you for your innocent presentation. Very nice presentation, very nice, beautiful presentation. Thank you, Radek.
Thank you, Alex.
I have a question. Can I speak?
Yes.
Yeah.
Go.
First of all, I would like to thank Radek Cibulka for your nice presentation in general. But well, my ask concern the general idea you had. You have some result about some form of weak covering property, because it is not a classical result like Grace and Lusternik, but you get some kind of weaker property, or at least some covering property under some mild hypothesis. Well, do you know whether there are some connection with another approach of this kind? Maybe for you it's different, but I mean the approach by two regularity. You know, maybe you know, the one proposed by Arutyunov and Avakov. Maybe they obtained something which is of course different from your result, but maybe you can recover within your theory their results in some sense. I don't know if you try to have some comparison to their results, and I don't know if there is some connection, but the general philosophy is like yours, because they can get some kind of weak form of covering surjection property under mild regularity assumptions. They do not need subjectivity of the approximation, and they anyhow they can recover some kind of regularity.
Yes, Amos, thank you very much. I like to see you here, and your question is precisely the point that when you have something like two regularity or this, then we haven't tried to cover precisely the results by Arutyunov and Quarters, but what we know is that you can apply simply this theory to have conditions, something like that you add here some convex set, yeah, so you obtain something like Robinson's results. Yeah, and in case of Arutyunov, here is a particular cone concerning connected with two regularity. So in principle, I think that it would be possible, but we haven't done this yet. Yeah, so just an maybe not satisfactory answer, but partial.
No, but it's just it could be a direction of further studies. This one try to recover also in some case in some form their results, just
yes.
for comparison. Thank you, Radek.
If there is, go on, Radek.
So, can I stop sharing?
Yes, yeah. Okay, so let's thank Radek for this nice presentation.